At this point, we can generalize our approach a little bit. And to be able to do that, we are going to make a definition here for linear homogeneous recurrence relations of degree k with constant coefficients. Now, every term here, well, this is a long name, but every term here has its own significance. You see, this is the general expression that represents a linear homogeneous recurrence relation of degree k with constant coefficients. Now, it's linear because the terms Tn and its earlier values, Tn minus 1, Tn minus 2, etc., appear just as they are. It doesn't appear in like Tn minus 1 squared or Tn minus 2 cubed, or let's say cosine of Tn minus 1. So they just appear as themselves and no function are applied to them. Therefore, this recurrence relation is linear. So when I say a linear recurrence relation, you should understand every term of Tn, or earlier terms like Tn minus 1, Tn minus 2, etc., appears just as is. Tn minus 1, Tn minus 2, etc., not as a function, or not inside a function, let's say. And homogeneous. Now, homogeneous refers to the fact that in this recurrence relation, we have no other function except for Tn's. We just have the Tn terms, Tn minus 1, Tn minus 2, up to Tn minus k. And therefore, we refer to this recurrence relation as homogeneous. And below, we have the non-homogeneous version. And when you look at this, you have another term here, g of n. It's not a function of t, but it's a function of n in general. Therefore, this here, the one below, is a non-homogeneous recurrence relation. Of course, it needs to be a function of n and not tn's, because if it's a function of tn, then it wouldn't be a linear recurrence relation. Okay, so what's next? Degree k. Now, this comes from the fact that you go as early as Tn minus k. So Tn depends on the value of this function t, which is observed, let's say, k slots before, let's say. So Tn depends on Tn minus k, and what ensures this is our assumption that Ck is non-zero. Ck, the coefficient of Tn minus k. Okay, so all the coefficients here, we allow them to be zero, but not this one, because then it wouldn't be an order or a degree k recurrence relation. And finally, constant coefficients. Obviously, it refers to these c values, c1, c2, etc., up to ck, are all fixed real numbers. So they are not functions of n, they are not functions of tn's, they are just simple real numbers. Okay, so like Tn equals 4 Tn minus 1 plus 3 Tn minus 2 minus Tn minus 5. So this is a linear homogeneous recurrence relation of degree 5 with constant coefficients. Now, if you have any of the Tn's in a function, then it wouldn't be linear. If you have an additional term that doesn't depend on Tn specifically, which might depend on n, then it's not homogeneous, it's non-homogeneous in that case. And if, well, the degree refers to the term where the difference between the index of Tn and the index of this term, whatever that is maximized, which is 5 here. And constant coefficients means all the coefficients appearing in this recurrence relation. In this case, 4, 3, well, 0 for Tn minus 3 and 0 for Tn minus 4 and minus 1 for Tn minus 5. These are all real numbers. So for instance, if you have something like Tn equals n times Tn minus 1, this is not a constant coefficient recurrence relation. Okay, so it's a homogeneous recurrence relation. For instance, it's of degree 1, but it's not constant coefficient. So in the remainder of this class, we are going to talk about linear recurrence relations of degree k with constant coefficients. We are going to look at both homogeneous and non-homogeneous cases, but we are not going to consider recurrence relations like this one, for instance. This is because this is not a constant coefficient recurrence relation, and to solve such equations, you need other methods that we are going to talk about.